In this video, we are going to talk about something unusual. We are going to talk about how chips can be connected with optics. Correct, Ashkan?
Absolutely, Robert. That's the very fun topic that I spend my everyday and weekends even working on. Yes.
Okay, so how does it work? I'm very curious.
So it's a very exciting field because the crux of everything that we do with all of our data, starting from the era of big data and moving into AI right now, is all about data. It's all about accessing data. It's all about moving data, computing on the data, and computing even in the data. And therefore, optics has a wonderful role to play in this field by making the movement of data lower power, lower cost, and therefore more efficient. And there's even more exciting fields of optical computing out there as well to try to accelerate some of the very task-specific workloads that are currently done in the digital domain with GPUs or CPUs. And by working on addressing the interconnect need, we hope as an industry that we can streamline and economize the assembly, manufacturing, fabrication, design, simulation, the whole the whole design flow of this technology to be able to reap these benefits. And so I thought I would spend some time with you today and your audience to talk a little bit about what is silicon photonics, what does it even do, how does it even work, how do I get my hands on it, how do I learn what it might be, what it might not be, how does one fabricate it, what does the hardware look like, and what are some perceived and real benefits. And so we'll talk about that with your audience for the next 45 minutes to an hour.
Okay, I have a question. So I'm very curious. Is this like really happening right now, or are there some chips which are really connected directly to optics? I know there is optical internet or Ethernet or these kind of
That's
things,
right.
but I never really seen chips connected through fibers or something like this.
Yeah, that's right. So you're correct. Since the middle 80s, the optical interconnect has worked its way from extremely long distances, initially from London to New York under the ocean, as you mentioned, all the way down through fiber to the home, inside of the data center, between racks and rack of switch to switch port, for example, switch to the server, server to server, and then now it's going inside of the server box, going from directly from the switch to the faceplate. And the entire name of the game here is to reduce the lengths of electrical traces as much as possible because of the power consumption that they are requiring as the speeds are increasing. So 50 gig NRZ, for example, on a PCB is a very difficult challenge. So if you can convert the signal to optics immediately from the package instead of going on the PCB, then you save that power. And this idea of co-packaged photonics has been pursued in industry heavily for the last probably 10, 15 years. And just this in the last year and a half, 2 years ago, there's been some major announcements from some companies. OFC, Optical Fiber Communication Conference, is a large conference for this field of work held in California, either Southern or Northern California, every year. And this last year, in 2022, Broadcom announced their initial co-packaged switch implementation. And then earlier this year, Broadcom announced the next version as well as Cisco. So here you see two major Ethernet switch providers who are actively, heavily working on these products to integrate optics deeper into their chip to exactly do what you asked, Robert. So yes, it's very much happening. It's very real. And it's about to start a whole flood of this technology into other switch or CPU or GPU in our case applications.
I think I know why this is happening. Just a couple of days ago, I was recording different video, and we were talking about PCI Express, how the
Mm-hmm.
speed is going up, and when we were talking about how important the loss in the PCB
Yeah.
traces and in the interconnection is, like, I can imagine that there are limitations. If we really would like to use PCB for interconnects, then there are maximum frequency limitations and we can't
Yes.
go higher. I guess that's the main
Yes.
reason why we have to bring the optics as close as possible to the silicon so we can go with the frequencies and
Yeah.
baud rate higher.
Yeah. The way I would say, Robert, is that copper signals, anything that's in copper, in traces, wires, whatever, um, interfaces between different copper media are low loss. So imagine a probe tip on a pad, or a bump to bump, or a bump to pad, or a C4 bump reflow onto a solder pad. Those interface losses are tenths of a dB or even lower. Okay. However, copper does not enjoy long traces.
Mm-hmm.
So if you have to go long distances, electrical signaling is poor. And this problem becomes especially difficult as you go higher and higher speeds.
So what does it mean long for higher frequencies? So, people can imagine like 1 meter, 10 meters.
Fair. That's a very fair question. So if you have to design a serializer driver to drive a 1 meter cable at 200 gig PAM4, which is today's state of the art, or even 100 gig PAM4, passive copper, for example, attached cables are limited to around 3 meters at about 100 gig and 1 meter for 200 gig. And that requires a significant amount of power. It's like 8 to 10 watts to drive that signal that long. If you have to do it on a PCB, it's easier and you could potentially drive lower power, but you always have to think about how many watts or hundreds of milliwatts your driver is consuming to go several meters up to centimeters across the PCB. And so conversely, the optical technology is the opposite of copper. In optics, interfaces are expensive. Going from the fiber into the photonic chip is expensive, as we'll talk about, or going from the laser to the optical chip is expensive. However, distances are incredibly cheap. Mm-hmm. So an optical signal can travel 2 kilometers without any repeating or regeneration of the signal. So an optical fiber that's in data centers used today has an attenuation of 1 dB per kilometer versus a PCB is 1 dB per millimeter or 1 dB per centimeter, for example, depending on what kind of material and core and trace design you do. Exactly, right? So that's what I'm talking about. Like copper, it's 1 dB, very minuscule amounts. Optics is 1 dB for kilometer. So distance-wise, optics wins, but then the interfaces are the opposite. Whereas in copper, a C4 to a bump pad is tenths of a dB. Fiber to a chip is 1 dB, maybe mm-hmm. even 2 dB. And so you have to use these technologies very judiciously. And so the idea is, look, if you have to go through a bunch of interfaces, do that electrically. But as soon as you need to go a long distance, do that optically, mm-hmm. because that's where it's cheap. And this is exactly the marriage of co-packaged in the different flavors, which we'll talk about of at what levels in your overall package do you integrate the optical engine at the board, substrate, interposer, or even monolithically inside of your core ASIC. These are all choices, design choices that should be made with this idea in mind of how many interfaces do I have and how long do I need to go?
Okay, so how does it work? We really connect directly on silicon to the processor? That's the closest how we can go, or?
Absolutely. So at the core of, so what we won't talk about really today is, and I'm happy to follow up on this, but what we would draw the boundary on is that the compute on the data happens electrically, digitally, mm-hmm. and that the data is generated digitally. Mm-hmm. And so your initial boundary condition is that you have a output buffer, mm-hmm. however long, however many bits you have, and you need to communicate that output buffer to a receiving entity's input buffer. And that's the crux of the challenge here. And so, traditionally you take that buffer and you serialize it using a SerDes. You serialize it, you communicate it through your channel, and then you deserialize it on the receive side. And what we are trying to do here is to say, okay, that communication channel, as much of that as we can make optics, we should, again, going back to that length conversation, because if I have to traverse that channel meter or 5 meters or 100 meters, I better do that optically. But if that SerDes channel is within my, let's say you're designing a GPU and you have different GPU cores and it's monolithic in the die, and your transmitter channel to the receiver is a few millimeter, well, maybe today it behooves you to do that copper. And so the output is electrical. And so then the whole point of this co-packaged optics engine is to convert that electrical signal into the optical domain. And how that is exactly done, once I share my slides with you, I can talk a little bit about exactly at the hardware level how that gets implemented.
Okay, so we can have a look. I'm curious.
Okay, great. So first, let's talk about what are planar light circuits. So there's been many different instantiations of optics, but the one that has the best chances of adoption in the CMOS industry is anything that is based in silicon, because it uses 50 years of CMOS fabrication methodologies and tools and ecosystem to actually realize the optical chips. And this is traditionally done on what is referred to as a SOI, silicon on insulator wafer. So you typically have very bulk silicon. So this would be something on the order of, for example, 800 micron thick piece of silicon. You have buried oxide on the order of 1 to 3 micron, for example. And then you have this very thin top silicon region, which is on the order of, say, 200 to 500 nanometers. So this picture is definitely not to scale. You get the sense that this is about 5 to 6 times thinner than this, and then it's on a bulk handle. But what this does is this gives you the vertical. So if we have this as the z-axis, it gives you the z-axis index of refraction. So silicon has high index here. So the typical index of refraction is, let's say, 2.8. And baried oxide is glass. So this is about 1.5. And here, this is air, for example. So it's 1. And so an optical signal gets trapped in this interface because it's surrounded by low index versus the high index. So this gives you the optical confinement. It's kind of like when you were a kid and you were in a swimming pool. If you look straight up, you can see the sun. But if you look at an angle, it looks like a mirror and it's going back into the bottom of the pool. In that case, it was air above you and you were in water, which is like 1.4. And so again, this is a very intuitive example of how light is trapped by index contrast. And so that gives you your Z, but then the way you get the x-axis and the y-axis confinement, and this is where this is fundamentally different than typical CMOS fabrication flow, is you do a topological etch. So in typical CMOS, in your very top silicon region, you create your P well and you create your N well, and then you put a gate and you put your gate contact and you have a transistor, you have a FET. In silicon photonics, you actually have to etch that silicon. So you create this topology, as I show here on the right, by selectively removing this portion of the silicon. And so, for example, if this overall thickness was X, this thickness here now is, for example, X over 2. You get a 50% or 70% reduction in the height. And what that does is it focuses the optical mode, the optical field in this region, because now, if you can imagine this shape going into the page, you create this ridge structure that looks like this, if you excuse my poor drawing skills. And in this picture, if there's light coming into the page and it hits this wall, it bounces off and hits this wall. And so it's confined. And that's because to the left and to the right is air, and in the center is silicon. So again, it's that same high index, low index contrast that traps the light in the XY plane. And so this then is referred to as a waveguide, which is the exact same microwave analogy to a copper trace in a PCB or in a dielectric, because a copper trace is exactly the same thing. It's also a microwave waveguide. All of these principles are the exact same, whereas in microwave, you're dealing with the gigahertz regime. Here in optics, you're dealing with the terahertz regime. So everything is a factor of 1,000 times higher in frequency, and therefore bigger, right? So a typical dimension of a silicon waveguide here would be like 500 nanometers wide, for example.
Okay.
That's what that would be the equivalent of a trace length of how wide is this thing on the actual chip.
So I have a question. So as you
Yes.
explain, basically this way you are creating traces for light.
Yes.
But
Correct.
now the question is why we would like to have these traces. So it's like we need to something transfer the light between the source of the light and between the connector which
Yes.
goes out.
Yes. For example, you can do that. So allow me to quickly add a new page in here. And so if we are now looking top down onto your photonic chip, let's say, so you have let me represent it as an input. So you have your laser in, and this is, you can think of this as like your VSS, your power.
And this would be like
Or
LED, laser LED or something.
yeah, that's right. It's a single wavelength source. And so the difference between an LED and a laser is that if you think about wavelength and power, an LED has a broad distribution. For example, that's why it looks like it's white, because it's, you know, all three RGB colors together. Versus a laser is much more concentrated at a single carrier frequency. So again, a microwave analogy of this would be that this is the carrier frequency of a radio station, which is like, let's say 110.1 megahertz in radio. In optics, it's 220 terahertz, for example. So you bring in this high frequency carrier. And now what you want to do is route the signal. So let's say what you want to do is use this and you want to bring it in and you want to create a 3 dB splitter, which again is basically a passive bias T, let's say. And so this is a passive 3 dB splitter, and then the first output and the second output. And then now here you want to create a modulator that actually encodes the electrical to optical signal. And then here, let's say you want to have a monitor because you want to see how much power is coming in from your laser. If it's too low or if it's too high, you can react to it because the losses are high or whatever. And then you take the output of your modulator and you route it to another one, where now this would be considered your transmitter output.
Okay, so basically what I was imagining, like I thought that you generate the optical signal exactly as the final signal, but that's not true. You have some kind of source of the optical signal, and then you need to have a optical circuit to process your electrical signal, add this to the optical signal, maybe do something a little bit else with this optical signal, and only then it goes out.
Right.
Okay.
So there's two classes of optical links, and silicon photonics for co-packaging is this way, where you have what is referred to as a continuous wave laser source. Basically, it's always on. And then you have in front of it a shutter. And so you just open the shutter or you close the shutter and you send that ones and zeros that way. Or you can do a thing where you have a laser and you turn the laser on or off. You turn the laser on or off itself. So it's like doing the light switch in your room directly, right? And there's different power implications. So for example, a laser is effectively a diode. And so the way that would work is you have this IV curve, right? So if this is voltage, this is current. And the way that you would modulate that is you would put this here, this would be your 0 level, this would be your 1 level, so this would be your, and so you would drive this voltage, this is V0 versus V1, and this gives you L0 and L1, like this. And this is exactly how transistors work. And so this was the first thing that we did as an optics community for the first 25, 30 years. We said, hey, we know how to drive diodes and forward bias because we do power amplifiers and radio transmitters. So why don't we do the same thing in the optical domain? And so the fact that this puts out light from the circuit perspective is completely irrelevant. It doesn't matter. You drive a voltage this way, and then it gives you a current output.
Mm-hmm.
In this case, it turns out to be light. However, this is very inefficient
Mm-hmm.
from a power perspective. It causes at a higher speed, it causes a lot of problems due to the physics of how a laser works. And so it gave birth to this other way of doing it, which is, hey, why don't I take my laser and bias it at the on level all the time, and then have an external attenuator,
Mm-hmm.
basically, and that external attenuator can encode my ones and
Mm-hmm.
zeros. And so now there's another benefit to it. In this world where you drive the laser directly, if I came to you, if you came to me and said, okay, look, I want to add other functionality to my laser. I want to be able to monitor the light. I want to be able to monitor the frequency, do all these things. You have to buy discrete components to do that. It makes the packaging very expensive. By doing an integrated circuit, which is exactly, again, what CMOS does, you integrate all these functionalities into one chip. So by having this planar light circuit, you can do a splitter, modulator,
Mm-hmm.
monitor, all other functions that you want, all in the same chip.
Mm-hmm.
So when the foundry is fabricating it, they don't care what's on the chip, it's the circuit.
Mm-hmm.
So you build in all these functionalities, and it's a lot cheaper, basically, to do scaling of function, scaling of channels, scaling of data rates, things like that.
So this picture is basically, or this circuit is basically mixed electrical and optical circuit working together.
Correct. And so now let's talk a little bit about, for example, how do you get the optical signal to react with an electrical input?
Okay.
So typically then there's, in this slide, we talked about this index of refraction of silicon. And so one way to change the behavior of the light is to change that index of refraction. And you can do that primarily through two effects. The first one is thermal. You can heat the material, which changes the material of the index of refraction, or you can use what is referred to as the plasma effect, the electron plasma effect. What that means is if you have basic silicon and you have light inside, the atoms in the silicon are moving and relaxing based on the frequency of the light. If there are extra electrons present, that relaxation and oscillation of the silicon atoms is slower because there's more charges to move around. And because it's slower, it's effectively a higher index, and the light behaves differently. So what you can do is the most classic device that was built it's referred to as an interferometer. Mach-Zehnder interferometer. This is a classical experiment where you split the light into two, and then you combine them back again. This, by the way, is exactly what can be done in the microwave regime as well. And so if you split the light 3 dB here and we combine it 3 dB here, you can imagine that you have two paths, path L1 and path L2. And so if the light that is coming in of a single frequency is traveling both of these two paths independently, if the phase difference between these two paths is 0 degrees, then you get constructive interference. So the light adds back onto itself, and if you put in one, ideally you get one output, no loss. If that delta phase is pi, or 180 degrees, you get perfectly, so this would be constructive, you get perfectly deconstructive behavior. So this gives you your 1, this gives you your 0.
So basically you eliminate, there will be darker.
Exactly, you self-cancel.
Yeah.
Because you are now interfering deconstructively with yourself. You basically 180 degrees out of phase.
Deduct two same signals, but opposite.
Exactly. So constructive interference would be out of path L1 and path L2, you see everything completely in phase. But deconstructive would be that the path signal out of L2 is now perfectly out of phase. And so in this case, you would get a perfect 0. Whereas before these two would add to each other, whereas now this one, and this one cancel each other out. So you get a net 0. And this is how you encode your signal. But you might be thinking, well, okay, if I build this physical circuit, if I build these traces on my chip, the length is fixed. So how can I possibly encode a phase difference?
Yeah,
Well,
that was my question. I wanted to know how
yes,
you are going to
yes.
influence the phase.
So the way you do that then is, whereas the upper path has length 1, it also has index of refraction 1, and the lower path has its own index of refraction. So for example, if I can selectively change the index in this lower arm only and cause a delta n,
So you
which
slow
would be
down the signal, basically.
exactly, if I define delta n as a difference between n2 versus n1, and if I can slow the signal down just enough to achieve pi phase shift and get it to be completely out of phase, then I have encoded my optical zero. And so you can then imagine that I have a transistor driver circuit somewhere, which is generating my data signal. So remember that buffer that we were talking about?
Yes.
So you have your buffer and it's fed into your serializer. And on the output stage of your serializer, you have a signal ground pin differential pair driving your however fast data signal. Well, if you just drive this signal into this electro-optical device here that can magically change that index of refraction, you will encode that signal into the optical domain. And what is this behavior? What is this magical device? In most cases, it's a simple diode. And the way that diode is created is, I'm going to recreate that cross section of the waveguide that we were talking about before. And I'll use some color here for helping us. So if you have a p-n junction, and this is a classic, what I would refer to as undergrad physics here. If you have a p-n junction, you have a diode, and here in the middle, you, as your theory will remind you, you have your intrinsic region, your depletion region.
Mm-hmm.
Okay. Now, in the P region and in the N region, you have a certain concentration of electrons. And then if you apply a reverse bias, this depletion region becomes slightly bigger. You remove some of those electrons. And so there is a delta in the population of electrons. So now with the reverse bias applied onto this diode, you now have lowered the number of carriers by pushing the boundary of this depletion region. And therefore, with less electrons present, the index of refraction is slightly lower. And so actually you speed up the light relative to this other arm who is completely unperturbed. And so in that way, you encode this. So now this has to have a certain interaction length. It cannot be instantaneously
That was my
short.
question, like how long it has to be.
Yeah. So typically then that delta n that we're talking about is like 1e to the -4. Or maybe even 1e to the -3 in some aggressive cases.
Of what?
And so
what?
Index of refraction change.
Okay.
Okay. So like if your index of refraction is 2.5 and you apply your bias, it becomes 2.4998.
Mm-hmm.
And so then you have to think to yourself, you have to put it in the basic equation that says delta, the L required is the delta n over lambda.
Mm-hmm. You need
And
to
so
calculate
you say, okay,
how long it has to be.
Basically, how long do these traces need to? So if you, for example, if you design a trace, I'm running out of room. let me erase this. So in your copper, if you're designing a trace on a chip or on a board, like let's say you have two different trace widths. One is like this and the other one is like that. Your microwave index here, let's say, is 3, and your microwave index here is 3.1 at Nyquist, whatever Nyquist is, 25 gigahertz. Then if you have a signal going into this one and a signal going into this one, after they go 1 millimeter, they're going to be different timed, right? For example, this one is going to look like this.
Mm-hmm.
These two edges are going to be different in time. So that delta T after a certain distance has to do with this delta N. And so you reverse that calculation. You say, okay, if I want my signal to be 10 picoseconds ahead of the other one, how much, and my length is fixed, how much index difference
Mhm.
do I need? And
Mhm.
so you design your traces to do a delay line or a speed up line. It's the same math here, just at a different frequency range. So this exact same equation here applies where you say, okay, based on the index difference that I can achieve for my wavelength of operation, this is the length that I need. So typically, these devices are about 1 millimeter to maybe 2 millimeters long, ballpark, given the state of the art numbers. So quite small, not very small, but manageable in size.
But that's
And
good to
so
know, because I was thinking like, is it like 100 micrometers or is like 2 centimeters? So you say
it
1-2 millimeters, that's.
it can be. So there are more aggressive device designs that are higher doping, they may require high voltage swing. So it's 1 millimeter typically with around 1 volt peak to peak
Mm-hmm.
swing. So if you can afford 2 volts, then you can afford this to be smaller. So it all just depends on how you optimize. How fast are you going? Can your output buffer drive 2 volts and your gates don't break down? All these design considerations are important here to consider, making a sweet spot balance between what the electronics is doing and then what the photonics can do.
Mm-hmm. So I have a question. So basically, in these new devices, you will have like only one source of the light, and then you somehow create your circuit based on this.
It depends. So it depends on how you want to do that. So um, it's advisable to think about the laser like a power supply.
Mm-hmm.
So if you can share that power supply rail
Mm-hmm.
with as many transmitter circuits as you can, then you can make a more efficient link.
Mm-hmm.
If you have to bring in external power for each of your transmitters, even though they're the same voltage, then you need more voltage regulators and you need more stable power supplies from the outside world. So again, if one laser transmitter can power 8 parallel links, for example, then you can make something that is 8 times more efficient than 8 individual lasers coming
Mm-hmm.
in. So yes, using these optical circuits, what we try to do is to spread that laser power across as many transmitter links as possible, mostly because lasers are a critical point of failure in the optical domain,
Mm-hmm.
largely because they are 3-5 material.
Mm-hmm.
So it's kind of like gallium nitride power converters. They work really well, but if they fail, they fail.
Mm-hmm.
And it's exotic 3-5 material, not in silicon.
Mm-hmm. Okay, another question.
Please.
So then if you have one source of the laser, does it mean you need to have two, for example, 8 optical cables going out, or can you somehow combine more channels into one fiber, or how this works?
That's right. So that's the other benefit of optics as compared to CMOS is that one physical medium can share multiple signals if they are of different wavelengths. So if you have 4 different wavelengths coming into your chip and you modulate all 4, you can combine them into one single piece of fiber that carries that data. And so that's a unique degree of data bandwidth scaling available to optics, is that as long as you have different wavelengths, you can put in multiple carrier signals into the same physical medium, and they won't interact at all with each other. They won't see each other at all in that fiber. And so one fiber can carry many signals. And actually, fiber to the home, WAN, and LAN networks do this. They carry hundreds of wavelengths inside of them, each one for my house, your neighbor's house, but all on the same physical fiber.
So
And
then you,
this, Mhm,
sorry for interrupting,
please.
then you somehow, how does it work with the frequencies? You somehow make them from the one laser, or you need to have multiple lasers, or?
You need to have multiple lasers. And so what the typical floor plan of that might look like is you have laser 1, 2, 3, and 4, and these are your carrier lasers, and they're brought into the chip independently. And then you have a modulator for each one. And then you have a very nice mux.
Mm-hmm.
that combines all four of these into one fiber.
Mm-hmm.
And so now this output fiber has lambda 1 through 4.
Mm-hmm.
And this MUX is simply a bandpass filter. It's the same exact thing as a microwave bandpass filter that says I have one input and I have a through and I have a drop. And you can call it a high pass or a low pass. You can design it both ways, but it just basically says if you're of the certain frequency, you go out this way. If you're another frequency, you go out this way.
Mm-hmm.
And you make them selective to these different 4 wavelengths.
Mm-hmm.
And then you can combine them all into one fiber and get it out the door. And then on the receive side, you have the reciprocal of this exact same device.
Okay, I was thinking it will be probably same.
It's the same exact device, yeah.
So you mentioned you can have even like 100 different wavelengths in one fiber. Then there are hundreds of lasers.
Yeah. Yes.
Or so there is a standard, or how does it work? I don't know. This frequency.
Sure. No, of course. So let's talk about that. So there is a existing standard, and I'll write it out, and we can kind of talk about it. So typically, because we started with directly modulated lasers, there's a standard referred to as FR4, and
it's like ECB,
right? And so this is an Ethernet standard, and what basically it means is F means far reach. This means it can go 1 kilometer or maybe 500 meters, depending on which version of the standard. And so this FR, and then 4 means that there are four wavelengths on a fiber.
Mm-hmm.
And so, for example, if you buy 100 gigabit Ethernet FR4 pluggable or transceiver, then you know by this definition that the aggregate bandwidth is 100 gigabits, that it has a certain reach of FR4, so let's say 1 kilometer, and that it is implemented by 4 lambda.
Mm-hmm.
And so it's 4 wavelengths, so 100 divided by 4, it's 25 gigabit per second each.
Mm-hmm. And they are exactly specified, so receiver and transceiver,
Yes.
Okay.
And this FR4 standard, and there's another one, for example, called DR4, which is a different implementation.
Mm-hmm.
There's, for example, ZR4. ZR means the reach is 10 kilometers. So again, same exact thing, just much longer reach. Again, just in the standards definition. All of these, however, have a delta lambda of 20 nanometers. And then the wavelength is 1270 nanometers, 1290, 1310, and 1330 in what is referred to as the O band.
Mm-hmm.
There's the C band, which is around 1550 nanometer. 1550 is the same thing as 1310. So there's minus 20, and there's plus 20,
mm-hmm.
also the same grid. So this is referred to as the grid. And so what this lets the vendors do is they say, okay, this is the grid. So I need to provide lasers that emit at exactly these
mm-hmm.
wavelengths. I need to design a MUX that has a bandpass filter at exactly these mm-hmm. center wavelengths. I need to design a DMUX. So everyone's standard because the grid is well defined. There are many other grids. We can spend another hour talking about that, but this is the common, like in Ethernet, what is used today in data centers and actually to your house, etc. There's other ones that are typically referred to, for example, as DWDM, where in DWDM, the delta lambda is on the order of 0.1 to, for example, 0.5 nanometers. This DWDM is currently used in telecom. So this is all about spectral efficiency. So here's a good analogy to also consider. At least in the US, I'm not deeply familiar with the rest of the world, but in the US, radio is on an odd tenth of a digit megahertz. So what that means is, for example, there's a radio station at 110.1 megahertz. and then a radio station at 110.3 megahertz. But there's not one at 110.2. That's because this is a carrier, and there are guard bands where you're not allowed to emit due to the FCC. Again, and this exact same principle applies to 5G wireless, 6G wireless, any radio communication, it all applies, right? So the same thing applies here. So you have a 20 nanometer channel spacing, but you have a 13 nanometer operating window because you have 7 nanometers on either, 3.5 nanometers on either side of the guard band where you're not allowed to operate. And so what you do inside of that transmission band of 13 nanometers can then be defined differently. And telco does DWDM because you want to have efficient spectral efficiency. So your fiber has, let's say, 200 terahertz of useful frequency range. What that means is like within the fiber, you can carry light across that entire frequency range. And so it makes sense to pack in as many wavelengths as you can.
How many you can put there?
So think about it. So 0.3 nanometers is 50 gigahertz. So the answer would be 200 terahertz divided by 50 gigahertz. Thousands of wavelengths can be fit inside of a fiber.
So does it mean then, for example, sorry again for interrupting.
No. I think I know what you're going to ask.
You may have like one switch, which is like special switch, and then you have these standard Ethernets with 1270 frequencies, and then this special switch will have only one fiber output with mixed everything?
It's possible.
Okay.
It's possible. It's possible to put, so if you want to design a 100 terabit switch, which is what the industry is working on today, and you want to put 100 terabits on a single fiber, mathematically, Robert, it is possible. Practically, it's very difficult. Because the Claude Shannon theory of bandwidth limit applies very much so here. Because as you, let me just get a new page. As you modulate your carrier, you generate sidebands. Just like you do in microwave.
Yeah.
So if you pack them too close, you can't modulate very fast. So your total bandwidth is a product of delta lambda times your data rate, let's call it data rate, divided into the total bandwidth of your fiber, for example. So you could do, for example, 50 gigahertz channel spacing and modulate it at 10 gigahertz. And you give yourself 30 gigahertz of sidebands. If you consider, right, if you're a 50 gigahertz channel spacing, you get a harmonic at plus 10, and then you have your other channel here, and he gets a harmonic at minus 10. And so between them here, you have 30 gigahertz of separation. So then what that means is you have to build a receiver filter that can do this. And then if you can't, then you pick up, this is crosstalk. And so this leads into BER issues and neighbor crosstalking, right? So
you can have crosstalk even in optics.
Absolutely. I mean, look, I keep saying this, optics and microwave are exactly the same thing, just at different frequencies. The same problems, the same issues are always there, and that's the beauty and the curse of physics. It's everywhere all the time. And it's the exact same principles apply here. So you can do a 50 gigahertz channel spacing in 10 gigahertz, and this, in this example, this gives you a 500G connection, or you can do 100 gigahertz channel spacing and modulate it at 20 or 25 or whatever, or 50, and just to make it even apples to apples comparison. Right. So in this case, you get minus 50, but then they're on top of each other. And so you realize, oh, shoot, or, you can do whatever. So you get my point. You have to optimize this on crosstalk, data rate, filter, shapes. All of these things are very, very important in this consideration of getting the light in the fiber. This is not a problem. This becomes a problem when you're detecting it, when you want to design your demux and your receiver circuit and to avoid all the crosstalk issues.
So I have another question. You say when you modulate it, but basically what initially on these very first slides, we were only talking about basically switching on and off the light. So we are only, are we really modulating this with some other?
Yeah, so technically you're externally attenuating this light. When you use this interferometer example that I drew in this slide, when you deconstructively interfere with yourself, you are attenuating your own signal. So this modulator is an attenuator.
Okay,
however,
but basically you only have one frequency there, or there is no frequency?
In the time domain example, if you, okay, let me answer your question more correctly. So if you have power versus time, you get ones and zeros in the time domain. But that optical signal, when it's being detected, falls onto a photodetector. And that photodetector converts the optical input to an electrical output. And it's fed into a TIA, a transimpedance amplifier. So then if this is optical power, if you look at photocurrent as a function of time, it follows the exact same shape. Now, if you do a Fourier transform of this, what you will see is a carrier and sideband. And it'll be a sync function.
Yeah, I understand this. Yeah, but for optics, is it
even
same
though, well, your eye can't see the optical signal. So what I would tell you, so if you Fourier transform the optical signal, yes, it's the same exact thing.
Oh.
Because you get the attenuation, and then you get this because when you modulate and you attenuate, you don't attenuate it with infinite extinction ratio. It's not that there's no light.
Okay, I understand.
It's just some low amount and then some high amount, right? And so Fourier transforming this optical signal gives you this exact same behavior. Converting it to the electrical domain, the current gives you the same behavior. So that's how you get the sideband. So it's not that there's no light at that frequency. There is some light. It's just 5, 10 dB attenuated versus the on state.
I understand. Okay, so I think we should move. We should maybe show something, because I had no idea this is going to.
This has been
so
very fun,
and we will not have enough time to finish everything.
And I'm happy to talk a bit more as we continue later on. But let's talk a little bit about what the hardware actually looks like. And so here I've drawn what for co-packaging implementations. Okay, this is what is referred to as the optical engine, where here in the bottom you have a C4 bump or a micro bump electrical interface.
So it's like balls.
Yeah, exactly. This could be C4 bumps. This could be micro bump. This could be an LGA, BGA, whatever type of a 2D uniform pitch electrical thing that you want to go into the bottom of this thing. And then at the very top here, you have an FAU, which is the fiber array unit. And so what this means is that your optical IO is vertical and or upward, sorry, and your electrical IO is downward. And so this is an engine that can get integrated into a package. And for the interest of time, I'll briefly talk about what is possibly inside of this thing. So typically in this box, what you would have is that silicon photonic chip that I showed in the first slide with the buried oxide and the silicon up here and some more silicon down here. You can possibly have through TSVs, through vias, or if it's on its own substrate, you can have a wire bond like this. And then there's a reciprocal electrical, or it's referred to as an EIC, which is basically a bunch of analog amplifiers. This is largely because the SerDes output that I was showing you earlier today has maybe a 0.8 volt peak to peak swing.
Mm-hmm.
That's what the most recent, latest nodes of CMOS can get for you. However, optical devices and some of these diodes that we mentioned earlier need something like a 1.1 volt peak to peak, maybe even 1.5 volt peak to peak in some cases. And so you design a separate set of amplifiers, linear analog amplifiers, that can just boost that signal a little bit more. And you do this because you don't want to burden your existing CMOS to do that high voltage. And so the electrical signal comes in here, it travels into this EIC, it gets amplified, and then it drives down into that PN junction in the silicon that we were talking about before. And the reciprocal works with the photodetector TIA back out. So these are advanced packages that get done at latest foundries where the CMOS chip is bump to bump integrated onto the photonic chip or bump to pad, depending on however you do that. And so that's how that quote unquote sandwich gets made. And then on this same optical chip, you have some sort of a light turn device that takes the planar circuit and turns the light upwards. Or sometimes the light goes out to the edge into a fiber directly. Or if it's going out vertically, it goes into a fiber this way. And so this is then that fiber interface that I was talking about. And so this is the anatomy, the basic anatomy of an optical engine. And then therefore, yes.
I have a question. So the optical layer, there is only one optical layer in the middle?
Typically, yes.
You can't really travel, like, easily travel. There are no vias for...
Well, that's not true. I should be careful. Thank you for asking that. There are foundries who are working on what is referred to as optical vias to have multiple optical layers stacked on top of each other. Industry isn't really pushing for that, largely because there's a lot we can do that we are not yet doing with a single layer of optical circuit. So from an R&D and advanced development perspective, working on multiple optical layers, I think is a wonderful idea, and we should go do that. We have a ways to get there before we actually need that. It's the equivalent of having multiple transistor layers on one chip. Could you do it, and would it be very difficult to build? Yes. And then if you had it, would you benefit from that? Definitely. And so it's a need versus cost trade-off at the moment.
Okay.
But very good question. It is fundamentally possible to do that. Yes.
So can we show you open picture so everyone can see how it actually looks physically?
Yeah, so here's an example from a press release from Intel, from Server to the Home website, where it talks a little bit about what the optical engine looks like. And so this picture that's up in the upper left corner, if you can see my mouse cursor, it has a fiber attached to it. Here you can see ribbons of fibers, which means it's a gang of 8 or 6 or 16 fibers coming in for the laser input, the transmitter out, or the receiver input, about the size of a quarter. And this is lidded in a substrate where I think on the bottom of this is some sort of an LGA grid, where that LGA grid then falls onto the substrate and it would get integrated on a board and on an entire package where you would have some sort of an ASIC in the middle. And then the electrical signal flows where this yellow arrow is, and then it gets converted to the optical domain and goes out via these black gray parts are fiber to fiber connectors, which is they just bring in the fiber connectors face to face with each other. And so this is a typical example of what an optical engine would look like. And I put a couple of cartoons together of, it can get integrated at the board level, on an MCM substrate, or even on an interposer at varying. And these pitch numbers are just estimates of like typically what kind of sizes we're talking about here. Like obviously it could be much bigger. And there's pros and cons with each of these flavors of the bigger the packaging is. For example, it can be socketed. It can be like an LGA grid for your processor, right? You can just open the lid, take the engine out, put another one in, close the lid, put your connector on. But then you see that it's a 350 pitch versus 150 if it was soldered onto the actual MCM. But if it's soldered, it's permanent. You can't service it. You can't fix it. That has certain other implications. Versus if it's in the package, it's extremely tight pitch. And designing an electrical trace on an interposer is much lower losses as opposed to going through
PCB.
MCM and board and PCB and all that stuff. So again, this touches back to the part we talked about in the beginning of interfaces and distance balancing. What do you need to be doing electrically and versus optically?
So what exactly you do? What is your job?
So I've been working in this field since starting with my PhD work in the mid 2000s, and I spent some time at Intel Silicon Photonics Group, and then at Hewlett Packard Labs, and then most recently at NVIDIA. And I started from the device level. I did a lot of work on the design of the silicon photonic devices, modulators, receivers, muxes, things like that, working my way up into understanding more about packaging and the CMOS design. And most recently, in the last couple of years at NVIDIA, I've been working as the product architecture role to identify pros and cons. Where do you integrate the optical engine? At what interface? What data rates? What size? How do you work on the fiber attach, the packaging, the CMOS design to make it optimized for the need, or exactly what you need to be doing for some of the systems that we build, which again is different. When you're designing a switch for Ethernet versus AI machines, the needs, the bandwidth,
I was
power
exactly
constraints.
thinking like, oh, it looks like it's all going to support AI in future because there is going to be so many data flowing around.
Yeah, that's right. And the reliability needs are completely different. The epoch of use is different. You know, in a cloud data center, quality of service to the user means something completely different than an AI machine where you use it for 10 hours or you don't, or it's an inference machine or large language model machine. So balancing all of those needs, requirements, power, cost, bandwidth numbers for some of the systems that we build is what I've been doing for the last few years. But it's been a wonderful career so far to learn about from the ground up. And it's an exciting time right now because we do have a very desperate need for power efficient interconnect solutions to meet the system's needs of the future.
I found this super useful because I had no idea that actually there are, or on the chips directly, we actually work with the light. I always thought it is just the source of the light and it goes immediately out. So you just,
yeah, it's
I
pretty
just learned
cool, right?
something new again.
I appreciate that, Robert. It's pretty cool, right? And like by doing this, by bringing in the light into the package and then manipulating the light inside of the package, it actually lays the foundation for doing even more very exciting things like optical computing, where you say that, hey, look, so one of the challenges, again, with one of the benefits of CMOS is that logic can be serially gated by the clock. So you do one thing and then you do another thing and then you do another thing. And because it's digital and it's passed from one stage to another, you have to worry about the timing mismatch between the digital circuits. That's what verification does. But for example, you don't really worry about the process variation. It's easy to synchronize that chain of machinery, basically. But the challenge is, or the drawback is, it takes you 20 clock cycles to propagate a logic flow, whatever that is. And so, hey, you have to wait, 20 clock cycles. That sucks. And so optical computing comes along and says, hey, I can do all 20 of those logic stages at once, simultaneously, at the speed of light, quite literally. I don't have a clock. I don't have to worry about a clock at all. The challenge, though, is across that very large, by the way, the digital circuit that I'm talking about is minuscule compared to the equivalent optical circuit, by the way. The optical circuit is 100, maybe 200 times bigger. And because it's bigger, the flops per area is very poor. But everyone says, hey, I can do what should be 1,000 clock cycles. I can do it instantaneously. But you also have to maintain coherency. What that means is that phase control that we were talking about has to be maintained through the entire photonic circuit. So this is an active area of academic research. There's a handful of very smart, very well-funded, very well-positioned startups that are exploring this effort. And it's all possible because we're working on this infrastructure to bring the light onto the chip. And so as you manipulate it and do communication, it's possible to manipulate it and to do computation. And where that trade-off is, where do you do optical compute versus classical digital compute? That's an active, open question. We have that debate internally and externally all the time at conferences. But that is one of the benefits that's possible by bringing the light in and manipulating, and it's quite exciting.
Okay, is there something else what we would like to mention? Because I
Yeah, I
don't
thought I
want to
would.
take too much of your
No, no,
time. I know
I
you are in
appreciate that.
hurry.
We can, I just want to put a couple of shout outs to the audience then on. If you are excited, please get a hold of me or Robert through whatever. I'm happy to talk more one-on-one with anyone. For anyone who wants to get is excited and wants to get involved, I want to share this with you. So MEEP is a wonderful finite element and finite difference time domain simulation for these devices. So if you're wondering, how would I ever simulate this thing at the pure physics level? MEEP is a very nice C-based open source. You can go download it today on Git and get all the code base and start simulating your devices today. And it's, I used it when I was an undergrad and a grad student, and in the 20 years almost since, the documentation has significantly improved. And so that's exciting. You can also use a lot of open source code similar to MEEP to generate the physical structure and what it looks like. And if you ever want to view it, K-Layout is a tool that's free. It's freeware, and you can view, edit, and generate these shapes. As you can see here, this is a snapshot of what looks to be a CMOS chip, but as long as you have layers defined for silicon layers, metal layers, doping layers, you can actually create your GDS or your mask set using such a tool. And that's a fun thing to do when you have your device simulated, but you want to actually do the layout for it. And I want to also talk a little bit about some of the courses. So this edX tool taught by my friend Lucas at UBC. I hope he thinks I'm his friend. I mean, he's a very nice guy. He's incredibly knowledgeable. And he has done a lot of good work at UBC in setting up this access to a somewhat challenging ecosystem on simulation, design, fabrication, test of a photonic device. So anyone out there who's interested in this, it is to be paid at the university level, but it is a great opportunity to get your hands on and to have access to a lot of information on how to get started. And similarly, AIM, Advanced Institute of Manufacturing and Photonics in New York, and here's a picture of Lucas down here actually. So he's involved with this entity as well. Here you can see, like, how do I actually, so if I've designed everything, can I give my masks to someone and have them actually fabricate something? And so AIM does a very good job on both education with a bunch of
these are
online
free,
courses.
I think you mentioned before.
Yeah, these videos are all free. As you can see, they're all hosted on YouTube. So it's a great chance to get in there and listen, to see and learn about what these folks are doing, and then getting involved in some of their MPW and prototyping services. So these are great resources. Again, if you have any specific questions, feel free to reach out to myself or Robert, and I'm happy to share along this information.
So thank you so much, Ashkan. This was like super interesting. I initially when we thought together, I was like, but what is going to be inside of this? Like, I had no idea, and now I actually finally understand a little bit more what is behind this electric and optics connection, and that's like super useful to know.
Thank you. Thank you for the opportunity to present to you today, Robert, and to your audience.
Thank you, Ashkan. And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEvel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.